So in this problem, we're told that there is a hydraulic press, and on one end, we are applying a force of 200 newtons, and on the output piston, there's an 800 kilogram mass. In this case, in the problem, it was told it's a car, okay? The result is that this car is lifted 14 centimeters up, and we're told that the radius of the pressure plate is 7.5 centimeters. Okay, we're asked, okay, what is the area of that initial pressure plate, the input piston? What's the work required to raise said piston 14 centimeters? How many strokes to lift the car? So one stroke, we go boom, 200 newtons. That's gonna raise the car by some amount. Okay, how many strokes to lift that car, the 14 centimeters? Okay, if one stroke of this causes this column to lower by 13 centimeters. Okay, and then this asks here, how high does the jack raise per car stroke? Pretty simple. So we're going to start with the area, and all my annotations will be in green. So for the area, we know that for a jack, pressure is conserved, so P initial equals P final. Okay, that's just a given. We know that pressure is force over area. Okay, so force over area equals force over area, or the force over area initial equals the force over area final. Okay, so we know some values here. We'll calculate what area is final. We'll call this side final, this side initial. Okay, so we're pushing down with 200 newtons. So it's 200 newtons. We're solving for A, the area of this piston. That's going to be equal to the force that's required to push it up. Now, what's the force of that? Let me grab a calculator. We know it's going to be this mass times gravity. So it's going to be 800 times 9.81. We're going to get that that's 700,848 newtons. Right? Because if the car's pushing down 7,848 newtons, to go up to any amount, we're going to need an equal amount of force going up. So that's why that is 7,848 newtons. Okay, and for the area, we have to solve this here. We know that the area, and assuming that this jack is a cylinder, we know that the area of a cylinder, or in this case, a circle, is going to be pi r squared. Okay, given that we know that area is pi r squared, we can take the 7.5, which we'll divide by 100. So 7.5 divided by 100, that is going to be 0.075 meters, which is the radius of our piston. We're going to square that value times it by pi. So we're going to get that the area here is equal to 0.0177 meters squared. Okay, so that's the area. So we'll go ahead and substitute that right here. Okay, so to solve for this, I'll have to bring area over to here. So I'll actually write this over here. So area is going to be equal to our 200 newtons divided by, and then we're going to take this whole chunk, divide it over. We're going to see that that's 7,848 newtons over 0.0177 meters squared. Okay, and that's going to give us our area. So the area of this is going to be equal to, and if I just do the plugging and chugging math, 7,848 newtons divided by 0.0177. Put that there. We're going to get that the area is equal to 4.51 times 10 to the negative fourth meters. Okay, that's pretty darn small. Okay, but that value will come in handy when we get down to these problems here. So the area of this piston is 4.51 times 10 to the negative 4 meters. Now for work, okay? This is just a simple calculation. Work is equal to the parallel force times displacement. Well, we're going up 14 centimeters. What's the force that we need, okay? And where's my calculator? Alrighty, so we know the force in this case is equal to the weight of this object here, right? It's pushing down, so to counteract that, we need the exact amount of newtons going up. So that will be 7,848 newtons. 7,848 newtons times 0.14 meters, right? Because 14 centimeters is 0.14 meters, okay? We're gonna simply just do a quick calculation, and we're gonna get that that's 1099 joules of energy. So it takes that many joules of energy to raise the car that much. Okay, so for number 3, we know that area initial times height initial is going to be equal to the area final, h final. So basically what this says is, okay, if I compress this by some amount, then this amount will go up. That's the conservation of volume, right? Because in an enclosed capsule, assuming that none of that liquid is leaking out, we know that this here is volume, right? Area of a circle times the height of a circle is equal to a cylinder's volume, okay? So we can just use that idea here to find, okay, so we're gonna push down on this some height. How much will it raise our, this here? So we know that the area is 4.51 times 10 to the negative 4 meters. And we say this because this will be our initial side, this will be our final side. And sorry, I would be solving for number 4 here, not number 3. Apologies on that. And then our height initial. So for every stroke, we go 13 centimeters, so we'll put 0.13 meters. We're gonna equal that to the area of this side, which is 0.0177 meters squared. And that should be meters squared as well. And then our height final is what we're solving for. So per time we stroke the engine, what is the height differential on that? So 4.51 times 10 to the negative 4 times 0.13 divided by 0.0177. We're gonna get, so for every single stroke we put in, per stroke, and this is what this math is referring to, for every stroke it's 3.312 times 10 to the negative 3. And there, sig figs don't exist in this classroom, so we won't bother about that. Meters. So you do that once, and it's gonna go up that much. So how many strokes to lift the car? 14 centimeters if a stroke is 13 centimeters. So if the jack is gonna raise by this much, we can just do a simple calculation where we take 14 centimeters and we're gonna divide that by the 3.312 times 10 to the negative 3 meters. And we'll actually put this in 0.14 meters, okay? And we'll just do the math. And we're gonna see that this here is equal to 42 strokes. So you need to do that 42 times to lift the car up by that amount. That is the simple explanation for this answer. There are a lot to this problem, holy crap. But hey, we made it through. If you liked, please drop a like, comment if you'd like, subscribe if you want to see more content like this. This is probably the hardest for algebra-based physics jack problems. So, alrighty, have a wonderful day.